Axions? What are those? Let me explain.
Axions are massless, spinless particles that serve as a good candidate for dark matter due to their stability, invisibility, and abundance in the universe. These particles were theorized in the 1970s by two brilliant scientists, Roberto Pichai and Helen Quinn, in order to solve the strong CP problem.
Hold up. What's the strong CP problem?
In order to understand the strong CP problem, we have to first start by understanding what CP symmetry is. CP stands for charge conjugation parity, and it means that if you swap particles with their oppositely charged partners and flip them in space, then the laws of physics should remain unchanged. In quantum thermodynamics, the QCD, the Lagrangian equation describing strong force allows for a term governed by theta that would violate CP symmetry. But if theta were truly large, it would mean that the neutron would have a measurable electric dipole moment. But experiments show that the EDM of the neutron is less than 10 to the negative 10th power. So why is theta set to such a low number by nature, even though CP violation is predicted by the Lagrangian equation? This is exactly what the strong CP problem is.
Scientists Pichai and Quinn found a solution to this.
Let's make theta a field.
In order to achieve this, the two scientists introduced the Pichai-Quinn symmetry, a new global chiral symmetry which would be spontaneously broken by a complex scalar field, which composed of a 1 over square root constant, a radial fluctuation, a VAV, vacuum expectation value, aka the scale at which the field settles when symmetry is broken, and an angular fluctuation divided by the VAV. The complex scalar field would break symmetry when the VAV equaled a non-zero value, aka when the field settled into the minimum of its potential.
Imagine that this ball is your potential energy, and this ball is your complex scalar field. When the complex scalar field is in the middle, no matter what direction you look at it from, it's always in the same spot, which means that it's in symmetry. But in nature, fields, particles, anything always want to reach the lowest energy configuration, which means that the complex scalar field will roll down to the minimum potential energy. And in doing so, it'll pick a direction, which means that it'll break symmetry spontaneously. Now, when this complex scalar field rolls down to the minimum potential, it'll fluctuate about zero. And these fluctuations are the axion fields. And since the axion field divided by the vacuum expectation value gives us theta, the axion field being dynamical makes theta dynamical, aka a field.
If we discover axions, not only would we have a real-life solution to the strong CP problem, but also a potential candidate for dark matter itself.